Okay, so last time we went over the histogram. We were analyzing the price, the appraised values of our art collection. We have 115 values, and initially we started with the basic statistics, minimum and max, the average, count, and the median. I mean, initially we see the minimum is 250, which is nothing compared to the max 110,000, with the average around 9,000 or 10,000, which is a little bit less than 10% of the max. So immediately we could realize or figure out that the maximum is simply an outlier if we kind of trying to imagine how the distribution would be. And the median is 5,200. That means out of 115, 50% of these items have a value of 5,200 or less, actually less. So that's where the midpoint is. But the question will still be, how is the distribution curve looks like? So for that, we do a histogram. So initially, you started a histogram between the min and max. You break it into equal bins, like we did here, 10,000, 20,000, all the way up to 100, and we ended up with this distribution list. So we noticed that almost 92% are less than 20,000. Then we go back and we break this up a little bit. So instead of going 10,000, 20,000, we do like 1,000, 2,000 with 1,000 size bin all the way to 15. And we ended up with this distribution, which gives us a little bit better idea about exactly how the values are distributed between the min and max. So with the histogram, we did the frequency, and also we did the cumulative percentage, which is represented in the graph by this line. So the frequency is represented by the bar chart, the column, and the cumulative frequency by the red line. And the cumulative frequency has always to end up to finish at 100%. Because at the end, the total of all the frequency should add up to, like you see down below, 115, which is the total of all the cells selected. You want the Excel sheet? Sure. Let me upload it. And to Blackboard. I think I have it there, actually. It's here. You may also, as we start going, you guys can also open the link in the class under week 7 as well. We're going to go through those. This file is this one. Okay, so you'll see the file on Blackboard now. Okay. So far, any question on histogram? I'm going to unmute.
Hello?
Yes, any question on this? So I'm going to put the sum of these. Good, 115. So this is how we verify we get everything accounted for. And on the second sheet, there's histogram output based on different various sizes of bins. It shows you how the histogram will look like. Okay. Before I continue to correlation and regression, there's a couple of functions I wanna show, because what we mentioned here about the median, that the median is almost a 50%, 50,000. Okay, let me mute everyone again. So now we have 115 values distributed between 250 and 110. And we know the median, which is basically, this is a 50% value, is at 5,200. Make this a dollar sign. But what about the 25% of the population? What's the first quartile, which is 25%? Second quartile, which is the median, is 50, or the third quartile. So there is a function for that. Let me move this down a little bit to create a little bit more room up there. So first quartile basically use the quartile function. So this is the old one. As I mentioned, Excel always evolves and add and expand the functionality. So the old function called quartile, and it's supported with up to Excel 2007. After that, they broke it into two. The quartile included or excluded is based on if you want to include 0 and 1, 0 100% or not. I typically use the included one. So for this one, we use the array. We need to select our data set. In this case, these are our value lists here. So this is our data set. This is the array. I need to select which quartile. So we have 4 values, 0, 1, 2, 3, 4. 0 is actually, you notice, is equivalent to the minimum value. Let me do it this way. Second quartile. Let me move this up a little bit. This is at 0%. This is first quartile is 25%. This is 50%. And then you have third. %, and this is 75%. So first quartile is also, this is max. And the second one is actually median. So the second value, basically I need to set, this is the first quartile, this is 1. This is number 1, 1950. This is number 2. You notice this is give me the exact value like the median. And this give me the exact value like the minimum. And this is the max. I'll use bluish. And this is number 3 and number 4. Okay, is it clear how this quartile function works? I'll move them down a little bit. Too big, use heading 2. Okay, is it clear? So, Pinaki, you want me to do the histogram again one more time? Sure. But before I go back to the histogram, any question on the quartile function? No? Okay, if you have any questions, just put in the chat. So let me do one last shot of the histogram. Hold on. This is manual histogram using count function. Okay, and this is the frequency. This is cumulative frequency. So this one, for you guys to take a look at it later, how the histogram basically is the foundation of it, how it works with the count. So this is manual. I'm gonna touch that. So we can go back to this histogram. We'll create another set of bins. We can use this again. Let me hide these. And I'll delete this and we'll do it again. So the bins we're gonna work on, hold on, I have a question. What if you want to more spread out more than 4 quartile? So I'll get to this in a minute. Let me do the histogram and I'll give you a more expanded function of than quartile. Quartile is limited to 0, 25, 50, 75, 100%. We'll do the bin experiment and then we'll go back again to another function. Show you how you can get a slightly different view of your data. So the bin we're going to use, basically, I don't have to put 0 because I put 1,000. That means the count for that is everything that's less than 1,000. Up to 15,000, after that it's whatever is more than 15,000. Maybe we can add this a little bit to, let me see, add it up to 20,000. Use this as our bin settings. So for the histogram, I have to go to the data tab and select the data analysis. Again, if you don't see data analysis here, you have to go to your file menu, options, and then on the options side, you go to add-ins, and at the bottom, make sure you select Excel add-ins and you click go. Go to new menu, and then make sure analysis toolpak is selected. By default, if you just installed Office, this is not going to be there, so you have to check it. Hit OK, and then this button will appear on the data menu. Okay. Then we click data analysis. We select histogram of all these statistical functions. And we need to select the input range, which is our data set. In my case, that's from H2 to H116. Now my bin range is this list. The output range, I want to select it right next to my bin. And I want it to include cumulative percentage and the chart output. It doesn't have to be arithmetic sequence. This is answering Henning. But it's better, it gives more equal sense, because when you see a column chart, you assume that the distance is the same. But it depends how your data is distributed, how you're going to present it. It doesn't have to be. And the bins, yes, get created manually. So this is the chart. I'll put it on the side. Let me scroll to the right a little bit and expand my chart. I'm going to delete the legend. It's pretty clear. So this is how my data is distributed between 1,000 and 20,000, and this is more. If you notice, there is one more column here, which is above 20,000. And by the way, just quick note, this list is not dynamic. That means if you change your data, you have to run that again. If you add more records, if you change any value, you need to go and run the histogram again. This is the one shot. This is based on the data when you run it, based on the data you had at that moment. If the data changes, the histogram is not going to get updated automatically. Meanwhile, this will, because this is linked formula. So if I change 47,000 to 57,000, this change, if you notice, went from 7.6 to 6.7 because one moved from one category to another. This does not. So every time you change the value, you add more records, you need to run it. And once you create the histogram chart, basically it's a chart like any other chart. You can change the settings the way you want. This is a percentage. I don't need decimal numbers here. And I need the major grid lines. And also, since also percentage, typically Excel gives you a little bit more extra leeway. I don't need 120%, only need 20%. And I can make it, the difference, the gaps will be up 125. That will give me exactly 25%, 50%, and 75%. So I'll put this up here. And by the way, you always can format the grid lines. You want to make them thicker. Going to change the color, make it black, and change the style. Okay. Now, if you want to try it again without the equal distribution, you can take the same bin, and let's say after 10,000, we can make it then 20,000 up to 50. And then you still can use this bin. It doesn't have to be equal. So I can come here and do another histogram with the same data set, but in this case, the bin will be, yes, it's this one. And the output, I'll put it right here. So there is no like one way, there's no rule how to select your bin. It depends on your data, how you're going to present it. It's whatever makes sense to your and relevant to the data. So I have the first shot between 1,000 and 10,000 up to here, and then these are at 10,000 each. So this is a little bit more logarithmic. Another question on the histogram? Okay. Now we'll go back to quartile. So quartile is limited to these percentages. I'll move this down a little bit. The other function that gives more flexibility is percentile. Let's see, I want to know what's at 0%, at 10%. Then I can use the function percentile. So I select the array, similar to quartile. I need to select my data. And then K, it's a free value. It has to be between 0 and 1. If you notice, 0 is the minimum, which is this case, same value like this. Let me use the same color. And this is the median at 50%. It'll be in green. Hold on, let me do the max in blue first. Okay. So to answer Jenna, you can do either one. You can reference a cell like I did here, or you can simply just type it as 0. Or you can put it has to be a decimal, not percentage, so 50% has to be 0.5. So if you want something more than just these preset values of percentage, you have to use a percentile function. Okay. Any question on this? Let me unmute you guys. If you're not talking, please mute yourself. Any questions so far?
No.
Good. Okay. Go back to mute. Okay, so we went over the histogram again. We looked at the quartile function, percentile function, how to help us look at our data. So this tells me 20% of my population has a value less than 1300. And you notice the 75% is 1250, which is between these two, because it goes somewhere in between. So hold on. If I wanna put 75% here, I should get the same Q3, 1250, as we see. And let me use the 25% as well. So, as you can see, this is pretty much the quartile function is just like a subset of percentile. The percentile gives you exact same function, and it's more broad. But this is like predefined and probably easier to use. So the 1300 is the same like the first quartile, which is this one. And this is this one, and okay, this is better. Now you guys can see the link. The 60% depends on of your distribution. 60% of 115 is not an actual value. So if you do 115 times 0.6, it's item number 69. Let me see if there's any value. So in this case, there should be a value like that. This also includes 0 and 1. So what happens, the way this function works, if there's no actual data, no actual item that matches that rank, it will interpolate between the two closest values. Yes, thank you. I highlighted the wrong one. So let's move on to correlation. Like this. Do some cleanup here. So correlation basically gives us a view. You know what? Let me delete this. So I have 4 sets of data, 4 series of data. I want to see if there is any link or correlation between these data. Do they change together or opposite of each other? So the function for that, we can do that in 2 ways. If I want to look at like just between 2 specific series, I can use the correl function. And that will give me a value between -1 and +1. A correlation closer to -1, that means these 2 series are inversely correlated. That means when one goes up, the other one tends to goes down, almost at the same level. If it's closer to 1 on the other end, it means if one goes up, the other one also goes up in the same direction. If it's closer to 0, it means they're pretty much independent. And the value varies between both. So we can build this correlation matrix manually. So correlation between series A and series A is always 1. It's the same series. So that's where you see those diagonals are always 1. So this is insignificant value. So we need to look for the correlation between B and A. And you notice B and A, or if you want to do A and B, is the same. It doesn't matter which one. So that's why the top right section of this table is also blank. So to check the correlation between series A and B, you select the first series, which is A, from A2 to A31, and then the second series, which is series B, from B2 to B31. And that gives me an index of 0.9, which is pretty high. That means these 2 series are correlated. Now, if I go look between A and C, the correlation is -0.96, almost rounded to 0.97, which is also pretty high, but with a negative sign, that means they're inversely correlated. If you go between D and A, it's closer to 0.14. So these 2 series are pretty much independent. Now we're done with A correlation. Let's see correlation with the remaining ones. B and C, -0.9, almost inversely proportional. And that makes sense because if B is correlated with A, C inversely correlated with A, that means C will be inversely correlated with B. And we can tell somehow now that between A, B, and C, they're either correlated or inversely correlated. That means, and D is independent from A, so pretty much you can guess it's going to be pretty much also independent from B and C. So between D and B is going to be 0.09, almost 0. Same with C. So, but instead of putting this function with each one of them separately, we can run a correlation analysis. And that by going to same thing, data analysis, we go to correlation. And unlike the correl function, we can select multiple sets of data. Actually, this is 25, this is 31. And here you need to mark that your data, your header, A1 to D31, includes the first row or not, is the header or the label. So in this case, I have the labels A, B, C, D, so I need to check this. The output range, I select here, and I hit OK. Well, let me cancel. There you go. You notice we ended up with the same values. Now, again, the difference between, just like histogram, this data is static. It's one shot. If you add more data, more rows to this, or if you change any values, these don't get updated. These will do. Let's say if I change any value in A, instead of 7, I put 18. You'll notice that all the values for A will change. Not by much, but will change because this is a dynamic function. They're linked. This will not. So if I change any value here in any of these data sets, in the whole range, I need to rerun correlation again. And also to get a quick view about how the values are, I can do conditional formatting. So green is highly correlated. Maybe I need to deselect the ones. I'll clear the rules from the selected. So if it's green or red, that means it's either correlated or inversely correlated. If it's somewhere in between, yellowish, that means it's low correlation. Viewer 37, whoever that is, asking if we don't have the same number of data. I think you need to have same number of data, but we can test it quickly. So if I delete these two from B, it's still going to work. So we don't have to have exactly the same numbers. I can run that again. Show you, but let's see how that goes. So data analysis, correlation, have the same set. So it still works, but it will be slightly less accurate. At the end, this is an estimation. Oh crap, I lost the values, but that's fine. And of course, you'll lose the formatting. Oh. So I need to select them all together. And then clear the formatting from these. Any question on the correlation? Okay. So what we can do, let me apply color code here. So we can create a line chart that represents these that will show us a little bit how the correlation works. So based on this, I know A and B are correlated. So let's try to chart them quickly with a line chart. Data points. So it's relatively clear here, how you can see that A and B, A in blue and B in red, they pretty much move in the same direction. You can check that too when you right-click on you select one data series and you right-click on it and you add a trend line. It's a linear trend line. It's the line in red. And same thing, the blue one, you add a trend line for the blue. They should be relatively parallel. They won't be exact because at the end these are all estimations. But just visually you can see it there, they move up and down relatively together. Now if I want to add C to the list, I can either right click, do select data and add a new series, or in this case it's even simpler. When I click the chart, the data selected that covers is highlighted, I can just include C and this will automatically include it. So C is in green. You notice, if you want to zoom in a little bit, if I look at, let's say, B and C, the correlation is -0.09, so almost -1. So you can see every time B goes up, the green goes down, and vice versa. The B goes down, the green goes up. So they're almost opposite. And same thing if I want to include D, you're going to see it's basically on its own, not really much of correlation between all of them. So when you put a line chart, it helps you visualize that correlation a bit more. Okay. Any question on correlation? If you have any question, please put in the chat window. Okay. This is a line chart. Let me do that again quickly. I'll delete it. So I select the first two, A and B. And I go to Insert. I can either click this button to insert a chart and select a line chart, or I can simply select it from here, the basic line chart. And I can add, once I select the chart, I get the data highlighted. I can either increase it to add C and D. And it's automatically detected that the first row is the title, the header, so they updated the legend automatically with colors. Any question on this? Okay. Good. So we'll move on to regression. Just quickly, before I forget, so on Blackboard, I put a link to, go back there, I think it's here. Okay. I already have it open. So this link here actually has pretty simple explanation, introduction to a lot of these functions. So it goes step by step. We're going to do that, but actually goes beyond also what I'm covering. So if you want to learn more about analysis toolpak, move and average, exponential smoothing, I'm not going to cover these now, but it's there to go over that. Okay. So let's go over regression and over a quick sample data. So regression, we have a sample data of a quantity sold for a certain price for certain advertising expense. So from a company's perspective, let's say if I spend this much on advertising and I sell for this price, this is how much I sell. So pretty much you can look at the quantity sold as output and the price and advertising are input. So this is my data. So I wanted to see if any relation, if the quantity sold is really dependent or strongly related to how much I spend on advertising is on the price. So we run a regression test. So this is the one I ran it before explanation, but let me push this down. Let me show you how we get these numbers, and we'll go back to this explanation. Oops. Okay. So same thing, I go to, again, data analysis, go to regression. So the Y range in my case This is the quantity sold, including the header, because I want to check that the first header is a label. And the input range is pricing and advertising. I put the output over here, and I would like to have residual and residual plots. Hopefully this will be enough space down there. Okay, good. So we get a whole this set of data about the R square. We're going to get the significance F, and we'll look at the p-values. What does that mean, and what are the coefficients? How are we going to read this? I'm not going to go over every single item, but these are the key elements to do that. Unless you're measuring in statistics or doing critical data analysis, then they will have more meanings to those. One other is the observations, like how many data elements we have is basically literally 7. Ideally, you would have way more than that, but the functionality is the same. So I'm going to delete these, or simply I can actually just hide them. And let me bring that up. So the R square, basically, the closer to 1, that means the regression line fits the data. So that's good, because if you end up with a low R square, you probably just want to stop there. Your data is not much linked together. So if you get R square close enough to 1, and then you look at the analysis of variance, or ANOVA. So significant F, I put the description here. I try to match the color. So if it's less than 0.05, that means the data is valid. If it's greater, so that means some of the inputs may not be relevant. So you may need to get rid of one input. Typically, you may have to have like 4 or 5, even 10 inputs here. So you may need to get rid of some and run it again. But how to determine that? So if the significance F is greater than 0.05, you may need to delete some independent variables. And that's basically, you can go to the p-value. If you have a p-value greater than 0.05, then that means that variable is independent. That means it doesn't impact the output. In our case, that's not true. Both p-values, as long as significant F is less than 0.05, that means they're all valid. That means a change in advertising will cause a change in price. So once we get to that point, now we need to look if quantity sold is a function of price and advertising, how does this change? So we know, for example, when you have a line y equal mx plus b, let's say 10x plus 5. What does this mean? This means for every change in x, y changes 10 times more. So if x changed by 1, y changes by 10. If x changes by 2, y changes by 20. So that's the coefficient of x. Here we're going to have the exact same thing. So the y in this case is quantity sold, and we have two inputs, price and advertising. But what are these coefficients? The one we just saw as 10. So the coefficients are given down here. So these three values that will give us the equation. So quantity sold equals, first the intercept. If you think yx plus b, this is the b. This case is 8,536 minus, this is the price coefficient, which is right here. So every time the price goes up by $1, the quantity sold goes down by 835. And advertising is, the coefficient is 0.59, almost 0.6. That means for every dollar spent in advertising, the quantity sold goes up by 0.6. And the meaningful of this is your function now. You can put different inputs. You can do some forecasting. Said, okay, if I spend this value on advertising and I sell this price, based on this regression test, how much will I sell? Is it clear? Any question? If any question, put it in the chat. But this is one of the most valuable tools actually, or utilization of the regression. If you have a lot of your sales data, you can run a regression test, and at least you can start identifying which inputs are really significant, impacts your output, and then what exactly the relationship between the output and the input. What is the function? Based on this, that's what you can do for, let me put this in bold. This you can use for forecast, because every test of this is costly, because you have to actually spend money and test with the price to figure this out. So once you spend enough money to collect the data, then you can do a forecast and start just experimenting with the numbers without actually doing this experiment. And it's faster. Any question? Okay. So the last thing is the residual output is basically based on this function. If you put these inputs, you're going to get like close enough quantity sold or output. So this will give you how much the residual, the output, the actual data is off from the predicted data based on your function. Based on all these observations. Of course, the closer they are, the less they are, the better. Any question on the regression? All good? Great. Thank you. So we'll move to analysis of variance. So analysis of variance, basically, I'm only going to use one type. This is the one way or single factor, but there's different ways you can do analysis of variance. It's to test a null hypothesis. If you guys all took statistics, which I assume you all did, the null hypothesis that the means of different series of or population of data are equal. So when you run the analysis of variance based on the F critical, the F value and the F critical, they will tell you if the means are, if your hypothesis, which is means are equal, is true or not. So again, you can go back to the link here has a simple explanation. So the mean is, of course, presented by the Greek symbol of mu. So we assume that the mean of series 1 equals the mean of series 2 equals the mean of series third series. So in this small example, we have, let's say, the salaries of people who have degrees in different fields, economics, medicine, and history, and the assumption is, the null hypothesis, that the mean of their salary is equal. So we need to test that hypothesis if that's true or not. So we go to data analysis. We're doing the analysis of variance. I think we'll do the one, we'll do a single factor. The input range, and we have labels. The output range we'll use, put it below. Hit OK. So the two values we're going to look at are the F and the F critical. So basically, we can put this in here. If F greater than F critical, that means the hypothesis is rejected. That means the means are not equal, which is true. So in this case, F, put it this way, we can say F greater than F critical. This will give me true or false. So in this case, the value is true. That means the means are not equal. But the trick is, these are three series. It's enough for one of them not to be equal to the other two or close enough so to call this off. The analysis of variance doesn't tell me which one is off or if they're all different or if just one is off. For that, you need to run a t-test. And the t-test, you have to do them one against the other. So for the series of three, you need to run 3 t-tests: economic and medicine, medicine and history, and then economic and history. See which one is the off one. So on a high level, this is the statistical significance between these 3 series. It's just basically you comparing the mean. Any question on this? Yeah. We're a little bit running out of time, but almost done. So the t-test basically is used to test the null hypothesis that the mean of only 2 populations are equal. So the analysis of a variance, you can add as many as you want, but the t-test is only between 2. So we take the same, we take actually different series for this one. So there's data collected about how many hours per week students study between male and female, and we're going to see if there is any difference based on that grouping. So we go to data, and again, it's all here. So we're going to follow these steps again, or you can see the recording. So we're going to go data analysis, and the t-test, 2 samples assuming unequal variances. The variable 1 is this one, variable 2 is this, and we have the labels. And the hypothesis mean the mean difference should be, we assume it's 0. Output range, put it below. So we got this data. Actually, you know what? Let me move it up a little bit so we can see all on the same screen. So the values we're going to look at, we have the t-stat. Let me highlight this. And the t-stat two-tail. So in our case, we need to check if the t-stat is greater. If the t-stat is greater than t-critical, two-tail, let me put this in bold so it's clear. Or if it's less than the negative critical two-tail, then the null hypothesis will be rejected. In this case, it's not. So the t-stat is kind of in between. So t-stat is actually not greater, it's actually slightly less. So we cannot 100% reject the null hypothesis. But also considering the small pool, the degrees of freedom, only 7. So it's also not 100% conclusive. But based on this small data we have, is not conclusive. Any question on the t-test? Okay, in the what situation we choose unequal variances? That actually depends on your data. By default, we use unequal sum because it assumes the variance is not equal. But if you know the variance is equal between the two series, and then you can use the other one. So the question is, under what situation do we choose two-side unequal variances? And the reference is to when we run the t-test, we have two options, assuming equal variance or unequal variance. By default is unequal. If you want to check the variance of a series, you can use the variance variable. So the variance, by the way, used to be two functions, var and varp. The variance, you can do the variance based on sample or based on the whole population. If you're selecting the whole population, you used to use varp. So this got changed to var.p and var.s based on sample. So in our case, this is the whole population, so we're going to use varp, and you select the series. So this is the variance of the first one, and this is the variance of the second one, and they're pretty off. So because the variance is way off, you select the t-test assuming unequal variances. Okay, and the last one is the f-test. We'll do it quickly. So the f-test is basically you test the null hypothesis of that the variance is of the population are equal. The t-test, we test that the means are equal. The f-test is the variance are equal. So it's pretty much exact same process. And you go to data analysis, to the f-test, select range 1, the second one, labels, output, like the output here. So you get your result. So quickly before we run out of time. So all of these functions, again, f-test, t-test, ANOVA, regression, correlation, histogram, they're not dynamic. If you change your data, those numbers will not get updated. You have to run those functions again to reproduce all these data. Okay. Let me unmute the call, and please, if you're on the phone, you can mute yourself if you don't want to ask questions.
Oh my God.
If there's more than one in the room on the call, please mute your phone. There's a strong feedback. Yes, I will post this on Blackboard in a minute, as soon as we're done. Okay. Guys, mute yourself. Mute your phone. Or if you're on the computer, mute your. This is better. Okay, so that'll be it for tonight. If you have any question, I'll be here for another 10-15 minutes. and I'll stop the recording. You can ask me a question on the chat room.